Hello, welcome to Chapter 10, first chapter and first section of second semester. We're going to learn about statistical inference and uh, confidence intervals today. Statistical inference provides methods for drawing conclusions about a population from sample data. And this will make more sense as we do some of it. But the goal with inference is um, to figure out what our data say about an entire population. Because we can't survey everybody in our population, but we can take a guess at what they would think. Now, a university wants to find the IQ of their freshman class. They obtain an SRS of 50 students out of 5,000, and the mean IQ of the group is 112. What can the university say about the mean IQ of the entire freshman class? Now, how would the sample mean vary as they choose more groups of 50? Well, we know that since it's 50, it should have a normal distribution, because since n is greater than 30. So the sampling distribution should be normal. The mean should equal the mean IQ of the freshman class. And the standard deviation, we know is going to be the standard deviation of the population over the square root of n. So I already started talking about this. Now, suppose we know the population standard deviation is 15, then the standard deviation for the sampling distribution is going to be 15 over the square root of 50, which equals 2.1. Now, the central limit theorem tells us that the mean is going to be, or the distribution is going to be relatively normal. So to estimate mu, we can use x bar from our random sample. And x bar probably is not equal to mu, so our estimate has some error in it. In repeated samples, the values show x bar follow approximately normal distribution with a mean of mu and a standard deviation of 2.1. And about 95% of that data is within 2 standard deviations of the mean. So 95% of the time, the mean IQ score, x bar, will be 4.2 standard deviations from, or 4.2 points from the population mean. So wherever x bar is within 4.2 standard deviations of mu, mu is within 4.2 standard deviations of x bar. So the unknown mu lies between x bar minus 4.2 and x bar plus 4.2 in about 95% of samples. So if we estimate mu lies somewhere in between the interval of 107.8 and 116.2, we would be calculating this interval using a method that captures the true mean about 95% of all samples. Alright, so this is what we call a confidence interval and confidence level. So our confidence level on the previous problem was 95, and the range that they gave was an interval. The confidence interval is collected from the data, usually in the form we have an estimate, and then plus or minus a margin of error. And you'll see this with presidential polls, or really any polls. They'll say Romney is winning at Florida 0.4. He's polling at 40% of the population, plus or minus 3. That plus or minus 3 is the margin of error. 40% is the estimate. All right. Now the confidence level, which gives the probability interval, will capture the true mean in repeated samples. So it's a success rate for that method. So in the 95%, so we don't know the sampling distribution when we take one sample. Our data could be here, 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 way out here. We'd have no idea. But we know 95%, so here's 20 samples, and 95% of the time, the error that we put in the 95% confidence interval will mean that the bars will cross the true mean. Now, it will happen every once in a while that we'll take a random set of data and get information that doesn't capture the true mean. But that should only happen about 5% of the time in a 95% confidence interval. Now, conditions for constructing a confidence interval. The construction of a confidence interval for a population mean, mu, is approximate when the data comes from an SRS, the sampling distribution is approximately normal, and the observations are independent. So when we're sampling without replacement, we got to say that the population size is at least 10 times our sample size. Now we need to figure out this thing called Z-star. Z-star is the Z value at which uh, we the Z value where we know the probability of everything underneath it. So for an 80% confidence interval, let's assume that 80% is in the middle. So if this is 80% of our data, then there will be a 10% over here and 10% over here. So what we need to do is find the z-score over here. So we want our z-score on that end. So there's 90% of the data up to there. So we can do inverse norm of 0.9. And that should give us our z-star. Now, for 80%, our z-star should be 1.282. Now, if we do this for 80, 85, all the way up, pause the video and see if you can find these values. So, and 99 is 2.576. Now, to find 85, these are all what I just had in my book, which were easy. You find if it's 85% of the data, 15 is on both sides, so that means we have a 0.075 there. So this is 0.925. Take the inverse norm of 0.925, and it should be somewhere in between there, 1.4-ish. All right, so when we want to do our confidence interval, we're going to do x bar plus or minus z star times sigma over the square root of n. So here's an example. A manufacturer of high-resolution video terminals must control the tension on mesh fine wires that lie behind the surface of the viewing screen. The standard deviation is known to be 43 volts. Here are the tension readings from an SRS of 20 screens from a single day. Construct a 90% confidence interval for the mean tension mu of all screens produced that day. Now there's 4 steps when doing a confidence interval. First, we need to talk about the parameter, then talk about the conditions, then do the calculations, and then finally interpret them. So the first thing we want to do is talk about the parameter. What are we trying to find? Well, we want to find the mean of all tension readings in a particular day. Now we have to check the conditions. It says the data comes from an SRS, so we can say data comes from an SRS. Wonderful, that's already done. Normality. We need to figure out if this is normal. We only choose 20 screens, so we can't use the central limit theorem. So we're going to have to graph these. So plug all of this data into your calculator and then make a box plot. All right, once you have all the data in there, then graph it, and you should have a box plot that looks something like this. All right. Now, This is about 250, 300, 350. So since this box plot is relatively symmetric, we can say that the data is approximately normal. So we want to write that. The box plot is symmetric, so sampling distribution is approximately normal. All right. Now the third condition is independence. So we're sampling without replacement, so we need to check that n is greater than or equal to 10 times little n. So that's the population has to be bigger than 200. So we'll just have to make a statement that says we assume there are more than 200 uh, video terminals being produced. Alright, so now we can move on to our calculations. So the first thing we need to do is write our formula. And if I do one variable stats, we can find our mean. And our mean was 306.3. Now our Z-star for 90% confidence interval is 1.645. Multiply that by our standard deviation over the square root of n, which is 20. And we'll get 306.3 plus or minus 15.8, which means that we have a range from 290.5 to 322.1. So now we just want to interpret that. We want to say we are 90% confident that that the true mean tension is between 290.5 and 322.1 for that day. All right, and there we go. We are done with our first confidence interval. Now keep in mind we need to write it up just like this in order to get full credit. All right, now you guys try one. Suppose you want to estimate the mean SAT score from for more than 385,000 high school seniors from California. You give an SRS to 500 California high school seniors. The mean of the sample is 461. Assume that the standard deviation is 100. Now construct a 99% confidence interval. Well, we want to start with the parameter. We want to estimate the mean SAT score of California seniors. Now we look at the conditions. Data comes from an SRS. We have 500, so since n is greater than 30, Uh, the sampling distribution is approximately normal. And we want to check to see that n is greater than or equal to 10n. So the population is at least as bigger than 5,000. And it says that in the problem, so observations can be treated as independent. Independent because big N is greater than 5,000. And it tells us that big N is 385,000, so we're pretty safe. Now for the calculations. I always like to write my formula first. So our X bar was at 461. I'm going to go full screen here. So 461 plus or minus our Z star. And our Z star for a 99% confidence interval is 2.576. And we're going to multiply that by 100 over the square root of 50. So now we just need to do the calculations. Alright, so the margin of error here on the right-hand side should be 36.43. So if I take 461 plus and minus that, our range should be from 424.57 to 497.43. So now we just have to interpret that. So we say we are 99% confident that the mean SAT score of all California seniors is between 424.57 and 497.43. All right. Well, hopefully that's enough to help you with your homework. Good luck.